Okay, folks. So today we will focus on few fundamental concepts of operating systems. So in this class and next few classes, we'll go through the basic concepts of OS and also architecture. I think yesterday I decided, after talking to you folks, that's important. Then we revise some concepts because OS and architecture are very closely related. OS, of course, works on top of architecture, right, or hardware. Okay, if we have a good understanding of architecture, then we will be able to understand OS. Otherwise, we'll have difficulty in understanding it, right? So the role of OS is just to virtualize all hardware and create very simple, easy to use solutions or APIs on which users programs can use to use hardware. Okay, so we will look at some concepts in detail in this week, and once concepts are clear, actually we are our job is done. Actually, we don't need to. If you are interested, you can go deeper into the topics, but usually sufficient. Okay, all right. So let's go ahead. So I have taken contents of this talk from two places. One is, of course, the first one is Berkeley course, and then second is of this book, Anderson and Dallin. And I have also sent you this beautiful book. It's available online. I've sent you a link today. Please go through it because this book is very beautifully written and it's based on Linux. Okay, however, if you really want to understand anything in detail, then follow this book by Anderson and Dallin because there's a huge amount of detail. There are 3-volume books. Whereas other book is very concise, precise, but you need to really focus on reading. So I use both books for this course. The good thing about the second book, which I'm telling, the 3 pieces book, is first thing is available online, it's free, and it's based on Linux. Okay, so if you read the book, you will automatically understand the internals of Linux. All right, so I am asking you to read chapter 2 from Anderson and Dallin and the one which I have sent to you. Okay, all right. So we will look at some of the concepts, not in great detail, because understand that we are trying to build concepts in this course, right? In the beginning, first 7-8 lectures will be only on concepts. Once you understand concepts, then life is very simple. Okay, for example, in architecture course, if you try to understand what all we have done is based on 5 or 6 principles, right? First, what did we study? So let's see. I mean, so I want you to start thinking deep and try to visualize what exactly is happening. Then you can go into greater details. Okay, this is exactly what I do. First, I try to understand what exactly is happening. Hindi mein you say kya ho raha hai? I mean, kaise ho raha hai? Okay, and then you go into depth and then explore the topics around it. Like with each piece of OS piece, there will be issues of efficiency and security. Okay, and once you understand concepts, you can see how these other 2 concepts can be applied. Okay, so let's take it for example. In the case of architecture, what are the fundamental concepts that we have studied that you need to know? Can anybody tell me about it? What all we have basic fundamental?
So about machine language assembly.
No, those are not the concepts. Those are actually details, right? Okay, you can say that these are concepts, but what is, of course, the whole higher level abstract that's given to you, higher level language converted into, actually we have not gone through the whole process. Assembly instruction, then machine instructions, then linking of that and loading. So this is the process, but fundamental we started with stored program concept, right?
Uh,
Stored program concept, right? What is it? Right, this concept, we studied a model, right? What was that model? Von Neumann model, right? Hello?
yes, sir.
Yeah.
Yes,
Yes,
sir.
sir.
So this von Neumann model is something that we studied in the beginning, that basically instructions and data both can be in memory, and then we read one instruction at a time using program counter, and then there is a memory attached to processor where we can store the results, or we can read instructions from there. So basically sequential execution of instructions. Okay, and there is of course IO also, right? So this is very basic, that when you write some program, it's always sequential, one after other. There's a model. Now of course, I mean, we can come out with different models later, but what's the second piece we have understood from the course? Basic concept.
Single cycle design.
Basically we, right, I mean, concept of pipelining. Okay, how in pipeline we can actually execute instruction, and that to different parts can do execution simultaneously, concurrently. Okay, so different parts of instructions, while one instruction is in execution, second instruction some activity is happening, right? So basically concept of pipelining, and you can also say it's instruction execution. Once you have this in mind, then we can go further and say that next thing that we study is how do we abstract the basic RAM or memory available to us to higher level program. Suppose when we write a program, okay, and if you are told that physical memory is given you only in chunk between 000 to say FFFF, and then second program somewhere else, and then your writing of program becomes extremely complex. Okay, and then you, even if you write in higher level language, then compiler's job is exactly start putting instruction, translate in such a way that only these memory locations can be used. Okay, so in order to give a virtual world to you as a programmer or a process, that the whole memory is available to the all the address space, whole memory is available. In address space, of course, has to reside memory, which we'll study now. Is you then, and each process can think that. Okay, so that is, and then actual practice, actual life is not so fancy and rosy, right? So there is a lot of things that keeps happening. Memory is limited. Then it has to be split across, or it has to be shared across multiple processes. So this changing, because your address space, which program things or process things available to it, has to be mapped somewhere in physical memory. And not everything that is in address space has to be there in physical memory. So only something that's needed can be there. So we studied the concept of virtual memory. Okay, then we have seen that memory is very slow. Okay, RAM is very slow, processor works at very fast speed. Okay, and if processor has to wait 10,000 or 100,000 cycles to get data for memory, then everything will be very slow. Okay, then we have studied the concept of cache memory. All right, and then we have seen that if processor has to do IO, then what are different techniques for that? That's all we studied. Now if, okay, so now you have to visualize. A very important thing is you should be able to, once you visualize, you may, what happens in the beginning, it takes some time. Okay, then once visualization is there, how things really operate, then it becomes very simple to build on that, right? Then you can think of efficiency, reliability, security, and all that. Okay, so let's focus on concept, and I would request you to please read from book, because sometimes what I teach may not click to you, but when you read from the book, because explanation is, in greater detail, it may click. Okay, so please, of course, this second book which I am telling you is nice, crisp. So after this lecture, if you go and spend just half an hour reading a chapter, is sufficient. Okay, so this is what we studied in last class. The OS provides us virtualization. Okay, and and virtualization in terms of all the hardware that we have is presented in the form of abstraction like address space or process or something, which on which user programs can which users program use very easily. Like, I mean, instead of telling that in the storage, which is nothing but disk, you have sector 0, 1, 2 up to 10 available, and ask user to use this disk, user will go mad. Okay, so this abstraction where something can be stored is provided to higher and using concept of file. Okay, all right. And we know that hardware is of great complexity. If I expand this, you can see that multi-core processors are available, and then we have, okay, just a minute. Okay, so we have memory channels, we high speed interconnection, actually, then high speed IO. For graphics, we need very high speed IO. We studied some of these concepts, like how buses are organized. Then DMA, direct memory interface to memory chipset. Then all these things are there, right? And this is becoming extremely complex as we go ahead, right? And at the same time, we have seen the software complexity is going very fast. Okay, in fact, the OS, and in order to meet this complexity, OS is also growing very fast, right? The first OS was very small, and we can see now the next generation of OS was significantly larger, and now the latest one is 5.3 is much, we can see is less than 20, maybe 15, 16 million, but now it's 27 million lines of code. Okay, so in fact, OS is also becoming what is a complex, right? In order to manage complexity. Okay, all right. And then OS has to manage all buggy, many pieces of software can be buggy. For example, device drivers. When you buy a printer, and then printer has a peculiar things that it will do, right? Every printer has a different functions, operations. So these companies that develops that manufacture printer also provide a device driver, and device driver understands what's happening in the printer and presents a view on top that can be used by OS and users, right? So so these are the kind of plugins. So now if the device driver provided by, say, a company is buggy, then OS has to manage that too, right? Okay, and you can see.
Sir,
Yeah.
could you please explain what is the exact role of device drivers?
Okay, we will study that in greater detail. Okay, there is one half a lecture on that. See, device driver is a software that knows the peculiarities of the device that is to be operated upon, say a printer, or for example a keyboard. If you design a special keyboard, then OS may not know how does it work, right? But still it has to operate. It has, so, or you create a new device altogether. Okay, a robo, for example, and that, so now OS is there, Linux is there, right? Okay, now you as a manufacturer has to provide a software which is very peculiar to the device that you developed, and then it also has to have some interfaces for reading, writing, management operations, and it's very simple API or simple interfaces. Okay, that OS can use. Okay, so that for OS, the printer X or Y or Z, although may have lot of features, the interface of that to application may remain the same. Okay, so that a software that interfaces a device and OS is a device driver. We'll study that in detail little later. Okay, we'll go into detail of it. So all right, so OS basically hides complexity, and basic concepts that we'll discuss in great detail in the course are the following. Threads will study, address space, files, sockets, etc. Right? Okay, all right. And we have studied in the last class. The design goals of OS is it provides abstraction because it hides all the complexity of hardware, presents a view, and also provides convenience of the user, efficiency, and then its role is also to efficiently manage the resources, okay, like CPU and memory, and also provides security by isolating multiple processes. Okay, for example, a malware or virus sitting in a machine is also a process, right? So it must protect one process from another. So we'll try to cover four concepts. Four fundamental concepts we'll start with is process, then address space, then thread, and the fourth is dual mode of operation. Okay, so these are the four things that we'll study in very brief, such that you have basic image or concept, and then we'll build on that. Okay, we'll have few lectures on process, and then address space we'll not cover in detail because we are already covered in fairly good detail in architecture course. Then we'll spend maybe 7-8 lectures or maybe 5-6 lectures, something like that, on thread, and dual or mode of operation will just spend some time. Okay, because it's just concept. All right, so first thing is that what is the role of OS? What is the bottom line? It has to run programs. Okay, that's the role. Otherwise, what we'll do, if you as a right programmer, you will have to then look at the memory, put the your code into memory, create some space for data, and do all that operations, right? Okay, so basic role of OS is to run programs, and then we can say run it efficiently, securely, reliably, or whatever. Okay, so now what is the basic process? You write a program using some editor. Okay, say for example you wrote a program foo.c. What's the next step? It has to be compiled and made executable after linking, right? Link all that's needed, and then you created a file which is a.out in C, or executable file which has various sections like instruction, data, and the format that we use for executable file nowadays is called ELF. Okay, executable and linking format. Okay, it's not as simple as something that's shown here, but has many more fields. But nevertheless, something that we have available after a.out, after compilation, which is executable, is this one. What is the next step now? This is still in memory. Note that this is a file, and this is there in hard disk. A file is, you think that it's in hard disk. What's the next step? Still we have not formed the process. This is a file. This is static. There can be thousands or millions of files in exe form in the hard disk. Next step is that you load this into memory, okay, in appropriate form like this, and then give control to program counter. Okay, which is program counter is here, this place, and then the first instruction that it will execute, you just point it out to that. And then is the role of processor, then what we ever studied in the last class, last semester. Okay, but note that how this thing is organized. So every process has this structure. Now different OSs of course have different way they organize this space. Okay, this space. Okay, maybe some way, some is Windows and Linux may have different way of organizing, but basic components are the same. Okay, now this is that we see here is address space. Okay, it's a of course we have not brought in the concept of translation yet, but so this is each process assuming that physical memory is larger than address space. So this is what each process will visualize that it has. So we can say a process consists of code that is in kind of execution. We'll come to correct definition little later, but this is when a program that is after that's exe file, when it gets loaded in memory, it will be in this form. Okay, all right. So it will, so in order to do that, what is done? So it will OS has to get some space in main memory. Okay, so it's find out what is free memory available, and then it has to load text section. It has to load static data section, the one that is here, or data that comes from a compiled file. Okay, and then it also creates area for stack, and we have seen what stack will contain, right? Various variables, etc. Are kept here. Okay, and then heap, and we discussed that what this heap is, right? The heap here is to, when you do malloc or you want a dynamic memory where you don't know how much more you will need, then heap provides that. In this place you allocate it for malloc, etc. Okay, so the concept is that at this till this point you have just program. So program, whether is a text program, a source program, or assembly, an assembled program, or machine instructions, or executable program, that is not a process. Once it is loaded in main memory in this form, which is ready to execute, and processor can start working on the first section, then it is a process. Okay, so process can be in the state of execution, or it can be a state where it's waiting for execution. We'll study that little later. Okay, so of course, we can see that operating system needs see that network speed is growing. It grown from 300 bits per second to 20 Mbps, and then OS has to manage that. It means that in 40 years we have network speed has changed 67,000 times. Okay, similarly, number of cores earlier was 1 core per CPU. Now we have more than, it's kind of a processor will have 8 core or 64 cores, right? So 10 times more number of cores have gone into a computer, and OS has to manage that. Similarly, cost per megaflop. Floating flop is nothing but floating point operations per second, right? So cost per megaflop or million instruction floating point instruction per second was in 1980s when I started my computer science was $100,000. Now it is 20 cents. There is a 500,000 times cheaper now. So it means that users are doing a lot more computation, and OS has to manage that. Similarly, RAM capacity has gone 1 million times, right? Ratio of computer to user has also increased by a factor of 200 in 40 years. And then OS is to design for availability, reliability, security, privacy, portability, and performance. All right. So we are still into basic OS concepts. We have not started looking at what we're supposed to do in this class, but nevertheless. And then needs are also changing. For example, when I started, we had to submit the job. First, we have to type the program, and then there were punch cards. Punch card are exactly in same sequence because each punch card will give one instruction, and then we'll have to go and submit it to reception, and then they will take our punch card, which are 500-600 punch cards, and run that, and that will read the program and then will compile and everything and run, because for instruction for running also is to be given in one of the punch cards, and then finally a result will come after a day. That used to be the process. I mean, and when they improved efficiency, we used to get results if submitted in morning by evening, because there are hundreds of users trying to do the same thing, and then each process was mechanical, used to take time. And then we had the concept of multi-programming, PCs came, and so on. In the future, we'll have to see how it evolve, because everything is getting virtualized, and then number of processors are also going up. Then storage is also becoming petascale. There is a data center cloud. So OS role is continuously changing. Okay. With this, let's start the first concept, which we already studied in great extent. So process is a program in execution. So till the time you keep the program in edited form or compiled form or executable form, is not a process. Process is when loaded to main memory and is ready for execution. Okay, or it is in execution. Okay. So it's a OS abstraction for execution is fine, but this execution environment has restricted rights. Okay, so each process can access something that is in that we have seen is part of address space. We cannot say it's a full address space, because part of address space will be also some OS routines or kernel software, part of kernel software. Okay, so it can access almost everything excepting restricted part. Okay, now it's address. We can define this with protected. It means that each process has its own address space. Each process has its own local variables, right, and so on. Okay, so it's a protected one, and this protection is given by this, that something that's accessible only to this process. So this address space contents are accessible only to this process. Let's say it's for P1, only this P1 can access this. Okay, until some sharing mechanism is provided, which we'll not discuss now. Okay, now each address space is one or more threads. We'll come to threads little later, but let's assume in the process, when you start a process, is just a single thread. It means a single program counter. Okay, single all registers have some value. That's it. Okay, so processor state is something that values of register, program counter, is stack pointer. So this defines a program processor state. Okay, let's assume in the beginning there is one thread, but a process can create multiple threads. Okay, it owns memory, address space, and then file descriptors and socket. So we can define process by many things. Okay, first is the processor state. Okay, so at any point in time in execution, if you take a snapshot, let's say it's executing some instruction, machine instruction, you stop and see a snapshot, and then you store this state somewhere such that you'll have to start from next instruction. Then what it will contain? It will contain all values of registers. Okay, it will contain program counter, where exactly in sequence the control is, or which instruction is getting executed, and a stack pointer. We have created a stack inside. Okay, and we have seen we are using one process calling another, one routine is calling another routine, or we are using concurrent, we are using recursive methods also. One, same, some functions are called multiple times. So we have multiple frame within a stack, right? So a stack pointer gives where exactly, which is at the top of this stack, which is in execution. Okay, so we have a program counter, stack pointer, registers that define processor state. Then we also have memory state, right? What is memory state? Values of various variables, etc., which is there in this this what do you call that, whatever is at the, when, sorry, program is loaded into memory, we have all this address space available, right? So it's there. Okay, because in the stack we'll save all these variable values. All right, so now so this state defines, so we cannot say that process is just program in execution and that address space with various contents of state or its corresponding states which are there either in processor or in the memory in this space. Okay, all right. Okay, so it is simplest classic case is sequential process. Okay, wherein first instruction executed, then the next, then the next, and then and so on, right? This sequential execution. So we can say a sequential process is a unit of execution, a unit of scheduling. Okay, CPU will schedule a process, right? So it starts with init process and goes on, and then different tasks are running, different processes are running, and CPU will take one task out and put another process into execution, right? So using context switching. So it's also unit of execution, scheduling. Okay, it's a dynamic, so it's actually a dynamic execution context. So this defines everything, right? It is not just address space, but the state that is stored in that address space, and also is a processor state. Okay, along with different parts of address space, which is code and heap and so on, defines a process. Is it okay?
Sir, could you please explain the last part again? The dynamic execution context.
Okay, so let's assume that you are running a process. Okay, and then CPU takes the process away. It says that you have run it enough, now other process will be loaded. Okay, so what all will define process at that point in time such that its state, because you have to start it from the next instruction, and then all the values of registers, etc., in the processor has to be the same when the process has to be brought back. Okay, because different registers, like all the registers you have read, has to be the same, otherwise results will be wrong. So all that information, all values of registers, and which instruction you are currently in when the process has been swept out or has been is moved out. So that instruction number also we have to note, which is nothing but a program counter value. Then let's assume that recursion is happening, same function is, a function is calling itself, then we'll have to also need a pointer to point to the last frame. Okay, and various values of variables. Because at program execution, what are we doing? We are storing something in memory, okay, or we are reading something from memory, right? So all these variables that we have created for during has also to be there when we rerun the restart the stop process. Okay, so all that state, which is a dynamic one, right, because it changes as time progresses, not the static values, right? Okay, so the instant we have swapped it out, what are all these instances are is called execution context. Okay, it's called dynamic execution context. All the information that's there in the stack, heap, and various values of registers, program counter, stack pointer, etc., are defined process execution context. Okay, now we will store it somewhere. When the process goes out, we will store variables, etc., are there in this address space. Okay, somewhere in the stack. And similarly, we have to store register values, stack pointer, program counter. They go to something called process control block, which we'll study later. Also, they in new systems, they also go to something called kernel stack. We'll study that little later, right? We'll not. So, all right. So this is the concept of program. Okay, so it has two key abstractions. First is, of course, we have studied that the process is not a binary source code. It's not a compiled code. Okay, executable code. It's instance of running program. Okay, all right. I mean, when it is loaded into compiled code is loaded into main memory, it will load text part, a code part here, which is binary code. It will create heap. OS will create it. OS will create, also it will create stack. Okay, where various variables can be stored. Okay, so now we can say that process has begun. We created a process, and when it start executing, then program counter, which is stored somewhere. Okay, program counter which is there in PCB will start execution, and now as keeps on executing, values of different values of variables will change, right, as part of execution. Maybe you'll the program is doing a malloc, so this will change, and you stop this at some point, and whatever the state of this, what are different values of variables, etc., etc., and various values of PC at that point in time, or stack pointer at that point in time, because these are to be stored external. Okay, this defines your instance of a running program. Explain. Process has to be protected from each other, and once process in general is just, there's no difference in process and thread if process is just one thread. Also, single instance of execution, only one instance of execution, then is single thread or single process. Okay, so it means that there is only one value of PC. If we have multiple threads, it means that they are in different places in execution. Okay, the PC value will be different, and the register values will be different for second thread, and so on. So we can, single process is nothing but single thread. Okay, it provides protection and isolation that we have already studied in detail, and then we will also study address translation, where we have address spaces that contains own data. Okay, well, in the process context, there are two processes, and P1 and P2, and the data that process P1 is using, there's various values of variables and global variable, okay, or static variable. That for P1 and P2 it will be different, okay, and P1 will not be able to access something in the P2 address space. Okay, there's the abstraction provided. So second address concept is address space that we have already discussed in detail. Okay, so address space is set of accessible addresses. Okay, so suppose we have 32-bit processor, or PC value is 32, PC size is 32 bits. Then addressable memory locations is 2 raised power 32. Okay, so all that a process can address. All right, and then address space is just not a memory locations, addressable memory, but also states associated with that. Like this, we have stack, and a stack will have variable, then heap, which will have some dynamic data, then some global variables and code. Okay, all right. So address space of process contains all the memory states of running program. What is memory state? The various values of variables, etc., right? Or global variables or static data, etc. All right. Okay. All right. So when we read or write into memory, what happens? Okay, all right. So it may act like a regular memory, or it may cause IO operation. Like we have seen, IO is done by reading and writing into memory. Okay, so it's again is a part of address space. Okay, those places which will act as something into reading and writing into memory, okay, or some IO operation, sorry, not, is nothing but a very well defined memory location in the address space. Okay, and if a processor wants to read into, if we say if we create a program counter value, something that's in OS space, it can cause a fault or exception. Okay, so this is what it is. You can see that these are processor registers, and then PC will point to current instruction in execution, and a stack pointer will point to the top of the stack or a stack frame. Okay, now remember that this diagram I have taken it from last year's classes. So each process thinks that it has complete address space for itself. Okay, so each process can use same addresses. All right, you can see that is exactly same address. So each process thinks it has all the memory available to itself, which corresponds to address space. Okay, and then it's role of OS to translate this into physical memory. Okay, so address space, if you see address space, that different OS will have different structure or format of address space, and then you can see here code is in one of these. Code is here, read write this. Okay, basically this read only code and data. Go ahead, only read only. All right, and then you have malloc. Static variables here, global variables here. Then runtime fit malloc etc. is here, and then user stack is here where you put various variables, and this of course is kernel's operating system's memory, and in between, when you are using shared memories, the shared libraries, see, everything that your process use has to map into address space. Okay, the shared memories also has to come somewhere. The shared memories are shared libraries, like use printf or whatever in C, so corresponding libraries will come here. So this is one structure. This is another structure which for the Linux defines it this way. It's very similar. So same code, initialize data or static, uninitialized data, then heap, stack, and the kernel part. Okay, all right. And then this address, because now you have loaded a process, and then this process, a processor always works in virtual address space. Okay, and then this has to be translated into actual physical address space or physical address. And this translation, there are many methods of translation. Something that we have studied is using page tables. Okay, all right. So this translation is something like this. So this is virtual address space, or address space, which is of course virtual. Okay. Okay, and when it is loaded into memory, okay, so a part of that will, part of this address space, which is blue in color, will come here. And then there is another process as corresponding address spaces here that can be loaded into different parts of physical memory, because in a physical memory there may be hundreds of processes, and each is using its own address space. So at this virtual address space cannot be given in continuous memory locations in most modern systems, right? However, there are older systems where this virtual space were given in contiguous locations. All right, any question? We'll stop here.
Sir, I have a little question.
Mm-hmm.
Sir, if two processes, like
Mhm.
we have multi-thread, so they share same library. So, sir, will there be two copies of shared library or just a one between two processes?
Okay, there are two processes using shared libraries. There are multiple ways of doing that. Okay, we will study little later something called linking, where is only at the runtime this process can be this libraries can be used. But in general, what happens is that this OS, even this OS area in each process is the same. Similarly, this address space or address locations given, not here, sorry, here is the same in all address spaces. Okay, what does it mean? It means that in
We can
this
virtually link. Yeah, we can virtually.
in this diagram, we are assuming that they are in the same location, and now they are loaded into the memory somewhere, and they can also be shared using page table if required. Okay, if the process, these shared libraries may not be used by other programs, so it may not be, but if it is shared, so finally they are mapped into a physical memory, and these are kind of pages. Okay, right now we are seeing it contiguous, but actually these are pages, right? Now it is question of doing this mapping such that each map tables, for example, corresponding to shared space points to the same physical block. Let's assume that this is the physical block here. Okay, so both tables may point out to the same physical space. So it depends on implementation, but that's usually the case that physical pages where shared memories are there. Okay, that those physical page to virtual address mapping or virtual page mapping can be done by page table. So if the both page tables, OS can help in that. With both page tables, the shared libraries look corresponding to same physical page. Okay.
Thank you, sir.
All right. Is it clear? Is
Yes,
it
sir.
okay? Any other question?